Good evening from Brussels. It's me again, Jean-Louis Van Bella. I'm speaking from Brussels indeed. I had posted my last video, I think 2 months ago, and I said it would really be my last one. Now, apparently, as you hear me speaking, it's not my last one. This might be the last one. The thing is, in the last 2 months, I've done some cleaning up a little bit of my papers and sort of also, tidied up things and to really make clear what sort of I understand and what still sort of needs to be solved in this weird world of quantum theories, because there's a lot of them. As explained in previous videos, so I have a bit of a realist interpretation of quantum mechanics. That's what I call it. It's based actually on, classical electromagnetic theory, and then, going back to some theses of Schrödinger, Dirac to some extent, Einstein intuitions were, in these discussions with these young wolves, Born, Dirac, Schrödinger, who sort of took over and created this world of, amplitudes and stuff. And a metamagical world almost. They lost that, historically speaking. I think they're coming back, and there's a lot of opposition against what is called mainstream theory. I'm not very hopeful that's going to end well. First, because what is mainstream theory? Every academic almost has his own theory, so there's not so much as mainstream theory. What unifies them, though, is sort of a belief in these virtual particles that vary momentum, energy around, intermediate vector bosons, and that mass sort of comes out of this magical Higgs mechanism, where if you push on it and you ask, like, what is this Higgs mechanism? Well, when you go to a party and then, people start to flock around one person, it's something like that. And I'm going like, that's not an explanation. In any case, I have done enough rants on that in previous videos, so I won't do that. But yes, sort of, I've been very much inspired by a physicist who is less well known, Paul Ehrenfest, and he complained that just before he unfortunately committed suicide, sort of depressed. You shouldn't take your research too seriously, I guess. That's what Boltzmann said: bring forward what is true, write it so that it's clear, defend it to your last breath. Boltzmann committed suicide too, also partly probably because he felt his vision on what nature really is and what it's all about didn't get much acceptance. From, sadly enough, from Planck, who believed in continuity and then sort of used his theory after his death to introduce the Planck constant and actually create what is now quantum physics. So Ehrenfest, Boltzmann, yes, they were right, but I'm not going to end up like them. I'm not going to defend to my last breath what I think is sort of true, what makes sense. I'm just presenting sort of my own personal journey to make yours easier when you sort of try to grapple with all the stuff that is around. So this presentation is actually really a bit of the last question. Sort of in previous videos I talked about, the model of an electron, a proton, what these elementary particles really are, the role of a neutron in a nucleus. Yeah, I'll talk about that. For the electron, the model was fairly easy. It's like this ring current. Let me, because that's in the other slides, let me start the presentation first by, what is it that we are talking about? What is it actually that, we want to understand? I said what we understand, of course, is what elementary particles really are, how they interact with each other, what is mass, what is energy, and how sort of matter particles, that have a mass, and an equivalent energy according to the mass-energy equivalence relation. So how do they interact then with light particles? You know, we have photons, neutrinos. What are they? Behind it all, I think, were Dirac's wise words. Dirac sort of also ended up very dissatisfied with how his theories have been interpreted. But then he wrote in the 30s these principles of quantum mechanics, and there's been like 3 or 4 revisions of that. The last was in 1958. And there he sort of reworked, not too much in his book, but he did rework sort of his introduction and his sort of conclusion, the final remarks on the very last page. I quote it here on page 312. It's quite a book. I went through it, but not too much in depth. There's better material around. But there he said really like, what is quantum mechanics? And he said quantum mechanics may be defined as the application of equations of motion to particles. That's also what Newtonian physics is. Newton's law, and we accelerate things, and we've got a system of particles and a system of systems, and you sort of keep track of where the energy goes, where the linear momentum goes, where the angular momentum goes, where all these physical measurable quantities, what happens to them. And so there's a number of conservation laws, conservation of energy, conservation of linear momentum, conservation of angular momentum, mainly. And yeah, that's what you do in Newtonian physics. The difference is that what he says here is the domain of applicability of the theory is that, we're not working with very massive objects. We're treating electrons and other charged particles, protons and the other nucleon, and sort of there's antimatter, there's sort of the same matter particles but with an opposite charge. And we're looking at equations of motion indeed, but yeah, these equations of motion, we're looking at how these charged particles interact with the electromagnetic field, because that's something we don't have an ether, we don't have a contact force. It's not like billiard balls. You push one against the other, and that the other ball is going to roll, and the other ball stops. Transfers its momentum and its energy. No, here we're actually particles interact, without a contact force. They interact with the electromagnetic field, and so the fields, they change because the particles move, and so the fields then make the particles move, and so we have these charges and fields that really interact with each other. And so the equations of motion there are given by Maxwell's equations, of course. But it's not like Maxwell's equations. It's often said that they break down at the smallest of scales. I don't think that's the case. There are theoretical arguments for that, but it's basically the problem with Maxwell's equations is that they can't deal very well with discontinuity. So they deal with like charged distributions or with currents, continuous current. But at smallest of scale, you have one charge and it's either here or it's there, and there's nothing in between. There's a field in between, of course, but and that's where Maxwell's equations, need to be complemented with the Planck-Einstein relation, where you actually deal with discontinuities. And so Maxwell's equations, they have derivatives in them and charge distributions and I said currents, and these are all continuous quantities, and we have vector operators and other operators that act on these quantities, these physical quantities. But yeah, these are derivatives, and they assume everything is sort of continuous. And at smallest of scale, things are not continuous. We know that, and that makes a lot of sense. Of course, you can't make things smaller and smaller and break them up in smaller and smaller parts. Some point in time, you hit the limit. You can have like fractal theory or whatever, but that's a bit of metaphysics then. And at some point it has to stop, and we find the charge. And also in fields, that fields are quantized. It's you can't have an infinitesimally small field, just like you can't have an infinitesimally small charge. So he said that. So the domain of applicability of our equations of motions, that's what we want to look at, is particles, charged particles interacting with the field, charges and field. And so he concludes that's a domain which, yeah, low energy physics and chemistry, you know, we know to deal with that, and that works kind of fine. But then high energy physics came, and high energy physics is basically about, you know, unstable particles, you know, huge collisions, enormous energies to, you know, very tiny things that collide into each other, and that's something they struggled with, sort of what happens. We get this like a car crash, two cars crashing, and then the pieces fly everywhere, and then sort of they recombine again in stable particles. So what happens in between? Now, that's what he says, that apparently there are, you know, other kinds of interactions. When he says other kinds of interactions, then he means, you know, not electromagnetic, nuclear, and then later, you know, there was some weak force who had to explain beta decay and all that. I think there are no real other kinds of interactions. You know, nuclear forces are in the end when, you know, they're electromagnetic. But in any case, that was his problem. He said these interactions are not at present sufficiently understood to be incorporated into a system of equations of motion. So he said, yeah, theories of them have been set up, much developed, some useful results have been obtained from them. But in the absence, and I think he's right, in the absence of really like equations of motions, where do the charges go, what happens to the fields, not sort of approximately, but exactly, then, you know, these theories, you know, are not very logical development of the principles that, you know, Dirac talks about in his book on quantum mechanics. So he says we're sort of in a pre-Bohr era, which what he means that before Bohr came and made sense of the atomic or electron orbitals, then you know, we were walking in the dark, and so then Bohr came and he shed light on, you know, what an atom really is, and how electron orbitals can be understood. So, but with these high energy physics, you feel we're in the pre-Bohr area. There has been no, you know, enlightened scientist or theory that sort of covers it in a way that is, you know, understandable and for everyone and clear. Something like Newtonian physics. But then, so he hopes that with increasing knowledge, a way will be found for adapting all these high energy theories into a scheme based on the equations of motion, based on equations of motions. And so then, you know, we can unify high energy physics and low energy physics. Low energy physics, where no such destruction of matter particles happens, where light doesn't get, apparently, because I have a problem with that, light gets created out of, you know, matter and antimatter pair, annihilation and all that. So that's what he said, these we need to find these equations of motion. But motion of what? And that's sort of where, well, this has nothing to do with what I'm saying. Well, it has actually. These are sort of 4 publications where I wrapped up things, where, you know, I work out, you know, what is a proton? What is an electron? We think of it as an oscillation of a point-like charge inside. The electron is a point-like charge, but, you know, if you push on it, you know, you have Compton scattering and Hart scattering, elastic scattering. So it's like a small point-like charge that are whizzing around inside of the electron, you know, and so when a photon comes, sometimes it hits that point-like charge, and sometimes it doesn't. It interacts with the electromagnetic field that whizzing charge generates, and then, you know, another photon gets ejected. The electron as a whole gets some kinetic energy. So once you sort of think about what an electron and a proton really are, and you think of them as having a structure, and that structure is an oscillation of a point-like charge inside, which Schrödinger said, he talked that this is actually, you know, that's the Zitterbewegungen hypothesis, where Schrödinger said, you know, there's like a secondary motion of something smaller inside, and once we understand that, you know, everything makes sense. The Broglie's frequency of a matter particle can be understood as an orbital frequency, and you know, a lot of other things. So the equations of motions are really the motion of that little point-like charge inside an electron and inside a proton. And once we understand that, how, you know, an electron, how it works, and how a proton works, and what the motion really is, then, you know, we can think about, okay, well, what is a neutron, and how we think of a neutron as positive and negative charge combined. So, well, what are their equations of motion? What are the orbital what is the orbital motion of the positive and negative charge inside, and so on and so on. One point that I want to make very clear is that we have negative and positive charge, but we really have electrons and positrons, and the positive charge in a positron and the negative charge in an electron, positrons and electrons are both quite big, and the positive and negative charge inside of them, it's related with the fine structure constant, is also quite big as compared to a proton and an antiproton. The negative charge in an antiproton and the negative charge in a proton must be much smaller, because the point-like charge in an electron and a positron is itself already much larger than a proton. We're talking, it's like another a deeper scale. We're talking the femtometer scale instead of picometers. So that's a factor 1,000. So in any case, these are papers where I wrapped up some loose ends. I have these lecture series. The last one I wrote, there was a 12th one, but it was more, is it like, can matter be made out of light? I think there's a lot of sloppy accounting going on. These virtual photons, gamma rays, but are they gamma rays? They seem to have some rest mass. I talk about that. So there's no, the thesis that there are charges and there are fields, that thesis stands there. And these are two complementary concepts that we need to understand also in the field of high energy physics. So I did a philosophical paper on that, because I saw Penrose came out with a new book where he says, consciousness can be reduced to this uncertainty principle and blah and this and that. The uncertainty principle is not an uncertainty principle. I mean, this uncertainty is not something ontological. We're talking statistical determinism. Things are moving around at very high speeds, at light speed, at smallest of scale. We don't know the initial conditions. So that's where amplitudes then come in. They are useful as a mathematical institute, but they're basically, probability distributions, because, we're talking systems that we can't define the initial conditions of. And so then that's a paper which is very easily readable and sort of concludes what I set out to do a little bit, is sort of what is the ontological basis for all that modern quantum theory. The papers I want to talk about, the one paper is sort of the proton model. So we have an electron model. I talked about that ad nauseam, as I would say, it's too many times already. But the proton, I presented that as sort of a three-dimensional oscillation rather than the electron being, an oscillation of a charge in a plane, a ring current just in a plane. With a proton, I said, we have another degree of freedom, and that explains why the proton, the force inside is much bigger. It's got a bigger mass, of course, also, but it's really like, we have an oscillation up and down, sideways, like we have in an electron, but we also have one sideways. So up and down, back and forth, and sideways. So, but I didn't give the equations of motion indeed. So how exactly, does that zitterbeweging charge inside of a proton, how does it zip around? So I'm going to talk about that. I just want to mention that, in the meanwhile, as I was tidying up, I did a paper on these intermediate vector bosons and the Weinberg theory, for which people got a Nobel Prize, where I basically dismantled that also as saying, like, look, you are building on an idea of, who was it, Fermi at the time, who also said, yeah, there must be a contact force, right? There must be an ether, because that's the same thing. There must be machinery and wheels and gears and what have you. And so we must have these quarks and intermediate vector bosons and whatever other virtual imaginary particle to ferry around this momentum. I dismantled that. I looked at the experiment, and so that's something interesting if you want to read. I think I really look at an experiment and I see, like, there's nothing there. If you push on things, sorry. The classical electromagnetic theory, where you have charges and fields again, and these interact, and that will do. That will explain, these high energy events that happen there, which in this case are like the interaction between muon neutrinos and electrons, heavy electrons, probably mesons, but that's also something that's not clear in the article. So, but the proton, yeah. So let's go to the proton. Before we do that, maybe again, quantum physics is all of physics. There's no contradiction between classical physics and quantum physics. It's just Maxwell's equations, you know, they don't break down, but they don't deal well with discontinuities. They work with continuous variables and derivatives and so on. They're actually, I should modify that, you know, there's like what they call the Liénard-Wiechert analysis, which actually can deal with charge, but okay, that's technical discussion. The easiest thing is just to, you know, try to understand the Planck-Einstein relation and combine it. So what I mean with that, well, here you have the electron model. You see that black ring current there. I will explain what the bluish and brownish and reddish lines are. That's when the electron starts to move. So we think of a ring current. A ring current, what is it? Well, it's not a continuous thing. It's really a point-like, little small zeta-beweging charge that spins around, goes around, round, with a cycle time and a frequency, which is of course the Broglie frequency. And we can calculate that. There's a cycle time t, and it's it's standard physics, the inverse of the frequency. And then we have the Planck-Einstein relationship, which gives us that frequency. You know, the energy, the equivalent energy, or you know, an electron has a mass, and then we have Planck's constant, the quantum of action, that gives us the frequency. And so the big mistake that was made, I think, is that de Broglie wrote down this relationship. He said, you know, matter particles, they're chunks of energy, and you know this. What is energy? Energy is a force over a distance. So yeah, these are oscillating things, a linear oscillator or something in plane, but that was de Broglie's thesis. The problem was that he thought about it in terms of a linear frequency, linear wavelengths, and I'm thinking, yeah, things go around and around. It has a frequency as well. So once you start, you know, for matter particles, you need to think in terms of orbitals and orbital frequencies, unlike for photons, where indeed you have a linear wavelength. So that distinguishes light and matter particles, really. So it's kind of strange they didn't see that, because it led to a lot of nonsense and wave packets that dissipate, all kinds of inconsistencies. So we think we've solved that. I mean, in our mind, you know, that problem is clear now. And we see we have an electron model where, you know, you can say the radius, I forgot an equality sign there, is you know, that zips around at the speed of light, and if we divide it by the frequency, then we get the radius of the oscillation, and that, you know, works out because we get the Compton radius of an electron. And so that's where the interpretation of the Compton radius, everybody talks about the wavelength, but you know, we can talk about the wavelength, but it's a circumference then, radius times 2 times pi. That's really sort of the scale above which you can localize an electron in a particle-like sense. But once you go beyond it, then you indeed have that little thing whizzing around. So that's where, you know, the electron, yeah, it's a particle, but it's a particle like at a scale indeed sort of the electron. Inside, you know, you have the matter wave, I would say, really sort of a mix of you know, point-like charge whizzing around, a field that keeps it in place, that generates, you know, the electromagnetic field that the ring current generates, creates a magnetic field, and that keeps it in place. So we have that perpetuum mobile. So Louis de Broglie's intuition in regard to the wave nature of matter particles was correct. But I said the big mistake that was made, and that's sort of, you know, I've got about 300 points now on ResearchGate in that paper, de Broglie's concept of the matter wave, you know, the issues that we have with it, that I see with it, because we interpret the frequencies as linear frequencies, you know, that's the mistake there. So it's a concept that relates to orbital motion rather than linear motion. So let's go back to that figure. So for the electron, everything is clear. We have the equation of motion for that point-like zeta-beweging charge inside of the electron. And then we sort of start thinking like, okay, now the electron is that ring current. When it starts moving, what is really happening? The thing what is really happening is that we add a linear component to that point-like charge inside. It's the classical electron. with classical electron radius, or it's also called the Thomson or the Lorentz radius. We start adding a lateral velocity. So we have the transverse motion, the planar motion, and now we sort of, get a spiral-like structure. It spins around, movement becomes lateral, but the thing is, nothing can go faster than the speed of light. So we're subtracting away from the orthogonal or perpendicular or lateral motion of that point-like charge. We add a linear, and now we can. I've analyzed that, ad nauseam again with the wave function and sort of what it really represents. So then, the faster it goes, the smaller that radius must become, because the speed, some of the speed of light is taken away from the x and y components. If the x and y plane is the lateral plane, then it becomes like this stretched out Archimedes screw, right? And then you can do all kinds of calculations that it explains, length, relativistic length contraction, time dilation, and whatever. And so I've worked that all out in that paper, and that fits. And the nice thing about this is that it really explains what we see happening. When you accelerate electrons in an electron beam, the radius does become smaller, their interaction radius. So it explains everything. It also generates, the model generates, well, the electron the current generates a magnetic moment, but our model does the same thing. We can apply a quantum mechanical operator and get, angular momentum. The angular momentum will explain the magnetic moment. There's no mystery about it. Often they talk about the anomaly in the magnetic moment, but that also can be explained by assuming exactly that a point-like charge inside of the electron is not infinitesimally small. It also has a small radius. And that sort of small radius and the anomaly in the magnetic, they explain each other. That's how we can give a theoretical argument for, the fine structure constant, basically. So it's all linked to each other, and that's fine. So for the electron, we're clear. And of course, that means that we also, for the positron, its antimatter counterpart, we are clear. It behaves like an electron, but with opposite spin. But we should never forget, that's because there's a positive charge in a positron and an electron. So don't abstract away from that charge that is there. Matter particles are charged in motion, full stop. And there's no mystery about it once you understand that structure. Now for the proton, it was a bit more complicated. For the proton, it said we have a formula for its radius. It's about 0.84 femtometer. I said much and much smaller than an electron, and even much and much smaller than a point-like charge inside of an electron. It's very small. The elementary charge in itself is the same, is the unit charge, just like for the electron. And so it means that you have a lot more force, a lot more massive. And part of the reason is that we think we have this planar oscillation for an electron and a positron. We're left, I often use Occam's razor, you have a degree of freedom in the system, and that must correspond to something real. Well, this is an application of Occam's razor. Something that oscillates in 2 dimensions, up and down and back and forth, it could also possibly oscillate, and that's a degree of freedom in space, left and right. And we think that's, proton has a different mass, much more massive, but also a different structure, a 3-dimensional structure. And so then you go okay, how do we model that? And then I've seen, this is the first figure. People are developing models now, proton models, based on the same Zitterbewegung hypothesis, which I don't think is a hypothesis. I think it's a fully consistent explanation of everything, at least of matter particles. And they say, okay, we need to add that extra degree of freedom and extra oscillation. And so this is an example of a proton model which adds that. The total radius of this toroidal structure, this helical solenoid, or whatever you want to call it, wrapped up in a ring, Yeah, you can see there's two oscillations. There's sort of that thing going around in a toroidal thing, and then yeah, that has probably a certain frequency. So that's like a ring current, right? And then we have that secondary frequency on it, which explains the rotation of that charge as it goes around the ring-like structure of that thing. So my problem with this is, yeah, that's a good intuition. That's great. On top of this, this model actually yields, the magnetic moment that we can measure. But yields, an equivalent mass that is the proton mass. So this model works. But is it the model? I was thinking more something like what you see, the blue figure there. Yeah, we have that spinning ring current, but then, it moves sideways. But then I was like, what happens? Is it really an accordion structure? Then you would have like sort of, how do you call it, a disk, but that gets extended. But it's not. I said the radius has to decrease when the linear velocity goes to the velocity of light, then the radius must become smaller. So I think it must be something spherical. And that's a big change from like 2-3 months ago. I thought it must be spherical. But it was sort of, I did a few, this is Desmos modeling tools, and I made that high frequency there, when it goes, the point-like charge, when it goes up and down, and it goes sideways, one orbital cycle, one cycle of that oscillation, there's no need for two frequencies. So we must reduce the number of loops, and that's sort of that black thing that you see. It can only be like one or two. In fact, it should only be one. And that's where I arrived at in the end. I started playing with graphing tools and sort of said, look, I really need to find that equation of motion for the point-like charge inside of a proton. That's where I said, actually, I'm wrong. In assuming a spherical model, it's going to be like maybe a double cone-like structure, the surface at least. And that's what I put on the right-hand side there. If you can see that these sort of Diabolo structure or two cones, because it's if you start from the left side, it goes round and round and round. That's actually where the lateral velocity, the sideways velocity, is zero. So when we talk about the linear oscillation, there must be a center point. It starts moving and accelerates around the 0 point. When it goes to the 0 point, it has maximum speed c, and then sort of it comes back. So there's a point also where the lateral velocity is 0, and then it comes back, speeds up, goes to c, stops at the other end again. So the lateral velocity and the lateral oscillation and that planar oscillation, there's like, say, like a phase difference, but it's not really a phase difference. Both need to sort of, it needs to go left and right and round in one full circle at the same frequency with the same cycle time. And that's where I put that figure. With the black line is half a loop. Let's go from, well, the left here, sorry. It's a mirror image. So let's go from the left. You see the charge going round and round and round. If it would be an electron, but it's a proton. So it has an oscillation, it moves, starts moving sideways, and it gains, starts moving sideways. Kind of weird with the geometry here. It starts moving sideways towards that center point, gaining lateral velocity, transversal velocity, and so the radius of that oscillation diminishes, but because it's just one cycle, that's really what it does. It goes to the other side, the other side continues, then it loses linear momentum, loses velocity in the x direction. So the xy plane is the lateral plane. So and then it starts refining its lateral orbital motion, and then on the other side of that figure it comes back. So we have like a figure 8. A figure 8 really, which I think models the which is the motion of that point-like particle in a proton. And it's a very simple geometrical thing. I said a figure 8. And you know, if you're gonna Google, I googled a bit. It's like what they call a Lissajous curve. Lissajous was a French mathematician in the 19th century who invented these things, and he basically said, you know, we can create these figure 8s and more complicated shapes by combining a sine and a cosine, two oscillations or two sinusoids. And they must have a phase difference, that's sort of, or not a phase difference, depending on the phase difference, 0, or pi over 4, or pi over 4, or pi over 2. A sine and a cosine, the phase difference is pi over 2. Then you have these, oscillations that have a more complicated trajectory, in this case, you know, like this figure 8 thing. But it's not that, actually, because I was thinking like phase difference. So there is a phase difference, but there's not actually. One loop when it goes around and one loop when it goes sideways, you know, one cycle, they must coincide. And so the loop must be closed, but at the same time the rotation must be in the same direction. That's what you see in this figure, and that's where you should really think about what you see here. So that black line, you know, it's not like it's crossing to the other side of the cone on the right hand side, this one, the cone. When it comes from here, yeah, I'm really confused with the mirror symmetry here. It doesn't go to the back of that three-dimensional shape that I'm trying to visualize here, these two cones. No, it stays on this side and keeps rotating in the same direction. And so this is a presentation of half a loop. It goes from left to right, or from right to left, if you want to reverse the direction. Have a loop, have a proton with opposite spin, and then it goes to the back of that thing, and you know, it's a figure 8, which doesn't cross over and then comes back. No, it is a figure 8 which sort of goes up and then goes up again, and then on the other side does exactly the same thing. So we have one loop. It is not a circle, but it's like a circle that, you know, bends inwards and then comes together. One loop, not two cycles, not two loops, no two different frequencies. And that's that was for me an aha erlebnis, in the sense that I thought like, whoa, you know, I have my model, right, which is like I call it the oscillator model. You know, it's Zitterbewegungen interpretation of mainstream. Sorry, Zitterbewegungen interpretation of quantum mechanics. I think the term has been a bit abused. It was revived by Dr. Hestnes in the 90s, but you know, I said there's a lot of interpretations around, so I prefer to talk about my model as, you know, an oscillator model. It's a two-dimensional oscillator for an electron, three-dimensional oscillator. You know, all degrees of freedoms in three-dimensional space are being utilized, and you know, and there's an oscillation up and down, back and forth, and sideways for the proton. So that makes it complete. There's not like a third or a fourth elementary particle. No, there's only the electron and there's the proton, and they have a different structure, two-dimensional versus three-dimensional oscillation. And also, you know, that point-like charge inside must be different. The negative charge in an electron is not the same as the negative charge in an antiproton. Otherwise, they would annihilate each other, and they don't. Protons and positrons, you know, they don't interact. Proton and antiproton, yes, because they have the same structure, and the positive and negative charge, they have the same size, and whatever. So you have really these four things. And so for me, it's clear now that for Occam's razor, which basically says that if you have a theory or you have a number of degrees of freedom in that theory, you know, each of these possibilities in your theoretical model must correspond to a physical reality, and vice versa. Each physical reality must correspond to something that is possible in your theory. So the theory is complete, and of course reality is complete. Or reality is reality. You cannot say it's incomplete. It is there, and whatever is not there is not there, full stop. But so your theory needs to be complete in the sense that all degrees of freedom, all possibilities in your theory, you know, they need to be They need to correspond to physical realities, and you need to be parsimonious in your concepts. That's the other aspect of it. Don't use too many concepts. Don't invent new virtual particles if you don't need them. We don't need them. We don't need intermediate vector bonds. We don't need a nuclear force. We don't need a weak force. The electromagnetic force inside a nucleus is much stronger, and that's why we call it nuclear. Something else seems to be going on, but it's not. We have magnetic and electric dipoles there in the nucleus, and that creates enormous electromagnetic fields at very close distances. And so that's what it makes it look as, there's something else. There is a force or a field that is not symmetric, asymmetric, and the densities change, and don't know. It's all pure electromagnetism. So that's what I wanted to talk about. I think I've done remarkably well. It's 40 minutes now, and I'm really done. And that's something I wanted to talk about. And you have the references on the first page. Go through the papers. It's kind of fun because I had fun with these papers also, because I really felt like, what Dirac once said. What does it mean to understand an equation? And Dirac said about that, I understand an equation if I can sort of see what its solution is. So, and I had this aha Leibniz with this as well. I have not worked out in detail, the parametrized function, which I should have, one parameter, and then, in a graphing tool like the one I've used for the other graph there, Desmos. No, it's actually, it's quite a complicated system of equations, relativistic equations, an envelope function, various relationships between, what I pointed out, this distance between troughs and crests, and the radius, which you can interpret, as a wavelength to make it circumference. So there's all kinds of complicated relationship. These equations are relativistically correct, but it so means with the Lorentz factor it becomes very complicated to solve this set of equations. But I can see the solution. This must correspond to it, and so I'm really happy with this thing, and I hope you will have the same aha Leibniz where you say, like, yeah, I understand these equations in a sense that I can see what the solution is, what the equation of motion is for the point-like charge inside of a proton. And I will leave it at that. I will see if there's